Engineered structures are often used to control the positioning of soil, water, or granular materials. These structures can take many forms, including dams, retaining walls, tanks, silos, culverts, and tunnels. To do their job successfully, they must resist the pressures applied to them by the materials they support. In this video, we focus on how these pressures arise and on the factors that determine their magnitudes. To understand how granular materials generate pressures on their containers, consider a box filled with wooden cylinders. Collectively, the cylinders produce a downwards force on the bottom of the container that is equal to their weight W. We could calculate this weight easily if we knew the weight density of the material in the container, a material property we denote using the letter gamma. In engineering, we often instead know the mass density, rho, of a material, and that quantity times g, the acceleration of gravity, gives us the weight density. The next step in our calculation is to determine the volume V of the material in the container. This can be found easily by multiplying A, the base area of the container, by its height h. To calculate the total weight, we simply multiply the weight density and the volume. When we substitute in the equations we found earlier for weight density and volume, we discover that the weight is equal to the product of the material mass density, the acceleration of gravity, the base area, and the height of the material. To calculate the vertical pressure, PV, on the bottom of the container, we simply divide this weight by the base area. Substituting in our earlier equation for weight and canceling the area term that appears in both the numerator and denominator produces a simple equation. This equation tells us that the vertical pressure PV is equal to the mass density of the material times the acceleration of gravity times the height of the material above the point we are considering. Notice that if we increase the height of the material, the pressure increases. It turns out that the wood cylinders also push against the sides of their container. If we stop pushing them together with our hands, nothing stops them from just pushing each other out sideways. To understand why this outwards force arises, consider 3 cylinders from the original stack. As gravity pushes the top cylinder downwards, it tends to squeeze between the other 2 cylinders, pushing them out sideways. The magnitude of that sideways force will depend on how hard the upper cylinders push downward, and that in turn depends on its weight and on the weight of the material that it supports. If the lower cylinders are constrained by structure, they will exert a horizontal force on that structure. At a short distance down, both the vertical and horizontal pressures are small. At progressively greater depths, both pressures increase. Experiments show that for most materials, the ratio of the horizontal pressure to the vertical pressure is constant. We call this ratio the pressure coefficient K, and it is usually less than 1. Thus, for granular materials, the vertical pressure at any depth is typically rho GH, while the horizontal pressure there is K rho GH. Clearly then, both the vertical and horizontal pressures increase linearly with depth, as shown in these graphs. The shapes and packing of the particles in a granular material affect the contact angles between them. Those angles and the coefficient of friction between adjacent particles determine the magnitude of the outwards pressure pH that is generated, and so they affect the value of K. If these ellipsoidal candies laid mostly horizontally, they would produce less horizontal force than if they were randomly placed or if they were spherical. Also, if the surfaces of either kind of candy became sticky, the lateral force would be reduced. As an extreme but practical example, sedimentary rock sometimes contains horizontal layers like those formed by these wood blocks. What horizontal pressures would they produce? What is the associated K value? Since gravitational forces are transmitted vertically from one wood block or piece of horizontally layered rock to the next, no horizontal pressures result, and K, the ratio of the horizontal to vertical pressures, is equal to 0. Liquids represent the other end of the spectrum. Experiments show that liquid pressures are the same in all directions, and so K, the ratio of the horizontal and vertical pressures, takes on a value of 1. In that case, we simply write that the pressure P acting in any direction at a particular depth h is equal to rho GH. So in summary, for granular materials, the horizontal pressure pH is usually less than the vertical pressure PV, as shown by these graphs and formulas. For water and other liquids, however, the horizontal and vertical pressures are equal to a single value P, as shown in this graph and formula. We can observe the pressures produced by granular materials and liquids by using this custom-made apparatus. It consists of a rectangular chamber with square windows attached to force gauges at 3 different depths along the side and 1 window and force gauge at the bottom. The gauge readings allow us to determine the horizontal pressure at 3 elevations along the side of the chamber and the vertical pressure at its bottom. Using this information, we can determine the horizontal pressure distribution along the side of the chamber and the vertical pressure at its bottom. When the chamber is filled with marbles, an example of a granular material, the indicated horizontal forces are 7, 14, and 19 newtons. And the downwards force on the bottom window is 33 newtons. And it is easy to see that the corresponding horizontal pressures do indeed increase linearly with depth. Based on a straight line fit, the horizontal pressure at the bottom of the chamber would be 2.2 kilopascals. The measured vertical pressure there is 3.3 kilopascals, and dividing the horizontal bottom pressure by the vertical one gives a K of 0.67. If we fill the chamber with water, the gauges again indicate a linear pressure distribution. To see how the pressures described in this video affect the design of real-world structures, we hope you will watch our videos on dams, retaining walls, silos and tanks, and tunnels and culverts.